suppose I have a clock pulse something like this. Okay, if the clock pulse is something like this, so we need to note some points which are related to the clock pulse. If we see here, this upper portion is nothing but this indicates the high level. High level means logic high. This is the clock pulse, and this is nothing but this is the logic high. Okay, so we can also say that high level. Okay, similarly, if you see this lower one, this lower one, we can call them the low logic, yeah, low level. Okay, so the low level is nothing but the lower logic, we can call it. But what happens? The problem is sometimes the suppose I have a flip-flop. Yeah, this is really important to understand. Suppose I have a flip-flop, and this is nothing but this is the clock controlled, and which we have already seen. Let us assume it is a set, and this is the reset, or vice versa, anything we can. Yeah, initially we consider reset and set, so let me do it like this only. And q complement. Let us assume I have a flip-flop having this kind of inputs and output. Reset and set are the two inputs, clock is one of the input, and q bar are the two outputs. Okay, and we know that if clock is activated and let us assume set is activated, then the output q will become 1. Okay, so what happens? Let us assume I have provided some clock pulse over here. Okay, if I have provided some clock pulse, and in this time period, whatever the time period I'm considering logic high time period, in this time period the reset and set becomes 0 and 1 respectively. So what it means, the output will be reflected, output will become 1, q will become 1, and the qt bar or q bar will become 0, because these both are the complementary in nature. But what happens? What I'm expecting that in each clock there should be one time change, so the data should not flip. Okay, so suppose if I have a clock pulse, high clock pulse, that will activate this flip-flop. Okay, and if it is activated, that flip-flop, and during this transition, without moving into the next high or low cycle of the clock pulse, if there is some change in the input, okay, if there is some change in the input, so in the single clock cycle, the output will become 0 or 1. So if the r become 1 and s become 0 without changing the clock pulse, because the clock pulse was, the time duration of this clock pulse was very high. Okay, if the clock pulse was very high, in that case what will happen? If there are uncertain changes in the set and reset inputs, so that will lead to change the output. Okay, and that can create the flipping of logic. Okay, so this is one of the problem that we should not consider, especially in the flip-flops. Okay, so let me repeat it again what I'm saying. Whatever the initially data we have, let us assume initially set was 1 and the reset was 0, and I have the clock pulse was logic high. Okay, clock pulse was logic high. So what it means, the q will become 1 and the q bar will become 0. But during the same logic high clock pulse, if there is some change in the inputs r and s somehow from here and there, okay, so what will happen? Because it will understand that because the clock pulse is activated, so I need to operate this flip-flop. Okay, so if it will understand something like that, so the output will be changed because there is some glitch at the inputs. So this is not acceptable condition. Okay, so to avoid that thing, what we can do? We can do two things. The first thing is, like, because the time period was very high, so the first possibility could be like this TS should be reduced. If somehow I am able to reduce this TS, might be we will get less chance to get the different kind of input patterns at the set and reset inputs. Okay, so this is one of the possibility to avoid this problem, but 100% we cannot avoid these things. Still, suppose I have initially the clock pulse width was something like this, and then I have reduced it to the 50%, but still there is a width. Okay, so if there is some change here at this time, and then again one more change at this time, so again the problem cannot be overcome, and we cannot make the TS close to 0. What it means, it required the frequency should be tends to infinite, and the infinite frequency clock is not possible. Clock frequency is not possible. Okay, so see, if you want to reduce this width, what it means, TS is going to be reduced. So it means the frequency of clock is going to be infinite. Okay, and this is not possible. Okay, so how to avoid these things? So whatever the discussion I just told you, this kind of triggering the flip-flop is known as the level triggered. Okay, level triggered means if the clock pulse is at logic high, so that we can call it the positive level trigger, because high clock pulse was utilized to activate these things. There is another kind of triggering, level triggering. Suppose I have a flip-flop and I have a clock pulse but with the bubble. Bubble indicates the inverted logic. So if I have a low logic at the clock, then it will be activated, otherwise it will not be activated. So this kind of flip-flop, we can call them the negative level triggered flip-flop. Okay, so in the clock I can have two kind of, one will be the positive level triggered and another will be the negative level triggered. Okay, a low level triggered. Okay, so see here, if any of the flip-flop is activating at the logic high, then we can call them the positive level triggered. Okay, so this is the example. This particular flip-flop is the example of positive level trigger. And this flip-flop, if I'm considering the bubbled clock, then we can call them, this is the negative level trigger. Okay, so these are the two things. So if I have a positive level triggered flip-flop, then those will be operated in this time period. Okay, so this is the time period where it will be operated if it is the positive one. Similarly, for the negative one, this is the time period when it will be operated. Okay, so this is all about the level triggered flip-flop or level triggered latches. Now, another kind of the flip-flop could be like, yes, I just told you, even though you are reducing this the pulse width or the frequency, increasing the frequency of this clock, 100% the glitch or this kind of problem cannot be avoided. If the change comes in between, then it can create the problem. Okay, so to avoid that things, we can go for the second kind of triggering mechanism. Okay, so I just told you we have a level triggered, and we can and the second one is the age triggered. So to avoid the problems that was associated with the level triggered kind of flip-flop, we can consider the age triggered flip-flop. What is this age triggered flip-flop? Let me tell you again. Okay, so yeah, I just told you in the level triggered we can have a two kind of triggering, either it could be positive or it could be negative. I just told you if the triggering is at the logic high, then we can call them the positive level trigger, and if the triggering at the lower or the low logic, then we can say it the negative level trigger. But what is the age triggered? Age triggered means what? I just told you to reduce this kind of problem, errors. We can simply reduce this width of this clock pulse. Okay, but 100% reduction is not possible. So one possibility, if you see here, there is a high to low and the low to high transition in the clock pulse. So if somehow we can utilize this transition time to make them triggered, so the problem which we discussed before will not come. Okay, so this kind of triggering is called age triggered triggering. So instead of labels, we will trigger the circuit at edges of transition, either from high to low or low to high. Okay, so if you are transitioning from high to low and the low to high, suppose I have a transition from low to high. Okay, so this is nothing but this is the rising one. Okay, there could be another transition from high to low, so that we can call it the falling. Okay, so we can have a two kind of the age triggering. Either I can trigger our logic during the falling, or the second one could be during the rising one. So if I'm considering the rising one, so this kind of triggering is known as the age trigger, and if I'm considering the falling side, then we can call them the negative age trigger. Now the question is how we generate these kind of signals. how we can trigger these kind of things. So I will tell you in detail how it could be done. Okay. So before the generation of those clocks, let me tell you what are the pictorial representation for the different kind of latches. Either it is the positive level trigger or negative level trigger, positive edge trigger or negative edge trigger. So let us try to see them. So if I'm considering the positive level triggers, the expression or the simple circuit looks like this one, where we have the clock pulse having the positive pulse which will activate this flip-flop. So this is the simple circuit. Second one could be the negative level trigger, where we need to keep the bubble. So if there are bubble at the clock pulse side, so we can tell them this flip-flop is nothing but this is the negative level triggered flip-flop. Okay, so this is the way how you can identify whether the flip-flop is negative trigger or it is the positive trigger. The third one could be, like if I'm talking about the edge triggered one, so how we can represent the positive edge triggered kind of flip-flop. So if you are keeping some triangle at the clock pulse, then it indicates the edge trigger. If triangle is present, then edge triggered. And if there is no bubble here, it means it is the positive one. And if you see the second one, negative one, so here we have triangle as well as the bubble. Okay, so if nothing is present, what it means, it is the positive level trigger. If only bubble is present, it means the negative level trigger. If only triangle is present, it is the positive edge trigger. And if both are present, then it is the negative edge trigger. So this is how you can differentiate different kind of flip-flops and their clocking mechanisms. Okay, so this is really important to understand how they are working. Now the question is, see, this kind of clock pulse are very easy to generate. Okay, so you can use the oscillator to make it like a clock generator circuit. Okay, oscillator could be one of the circuit that can be used for this purpose. But how we can activate any circuit with this one? Okay, what is the circuit before this so that it can activate during the transition, positive transition or negative transition? So let us try to see it. What is the internal structure of those circuits? Okay, if you can recall, you may have gone through some of the circuit like differentiator or the integrator. Okay, you know these things. So if we have any the pulse, and if we try to differentiate, if I have a pulse something like this, and if I'm passing through a differential amplifier or differentiator, then the output is nothing but this is something like a spike. Okay, so during the positive it will be something like this, and during negative it will again something like this. So there are some capacitors that charge and discharge. So the structure looks like this one. So we can utilize the differentiator for this purpose. So let us try to see how the differentiators look like. Okay, so this is the simple circuit for single stage differentiator circuit, where we have a capacitor, we have one resistor, and if I am providing the input something like this, if I am giving the input like this, okay, then what will be the outcome of this circuit? The outcome of this circuit will be something like this one. So it will charge, and then resistance will be during the positive cycle it will be charged. So the charging time constant will be as small as possible because we do not have any resistance here. So the charging time constant will be very small. Okay, so it will charge immediately. Now during the negative one, that capacitor will be discharged through this R, and this R decides what will be the discharging time constant. Okay, so it will discharge something like this. Okay, it will come something like this, and again during the negative pulse, like if it comes to the negative cycle, let us assume it is the 0, so positive negative, so again it will charge and discharge and so on. So this is the outcome of this circuit, and this is nothing but this is a differentiated one. Yeah, if you see the expression, if you can find the transfer function of this circuit, the transfer function of this circuit is nothing but this looks like a differentiator. Okay, You can check it out how the transfer function look like. Output divided by input. So output is nothing but R divided by SC plus R, something like that. So if you want to write in terms of the Laplace transform, so it will be something like that. So the charging and discharging time constant, you can make it. Okay. So this is how the generation of can be done. Okay, so now suppose if I want to make it only the positive trigger. Okay, so the positive trigger, how it could be made, like with the positive trigger only. So positive trigger can be made if I somehow I can remove this negative pulse, then we can make it the positive one. Okay, so we already know the diode is one of the circuit that can pass logic high. Okay, and if I am providing logic 0, so it will block. Okay, so if somehow I can connect one diode to this circuit, in that case the positive cycle can be passed and the negative can be blocked. Okay, so the updated circuit could be something like this one, where we have a capacitor, we have a resistor, we have a diode that can pass the positive one. So if I have an input something like this, okay, at the end I will get the output something like this one. So here, from here, if like I have connected one differentiator just after the clock pulse, then it becomes the positive is triggered flip-flop. Okay, there is some problem, there is some glitch here, so I need to remove this. Okay. So I hope the doubts are clear. If you have any doubt, you can ask me the questions. If you have any doubt, you can tell me the questions. Otherwise, we can move ahead. So this is how we can generate the different pulses. Okay. Now, so yeah, so this is how we simply, so what it simply indicates, it simply indicates that suppose I have the positive level trigger, and if I want to make it the positive is trigger, so what will happen? Before this clock, I have to add one differential circuit over here. Okay, so differential circuit should be added after the clock and before the inputs, this one. Okay, so this is how we can solve this one. So this is nothing but this is the differentiated out differential amplifier. Differential circuit. Yeah.
But sir, why are we using this differential amplifier?
Differential amplifier is basically used to generate the spike, because I just told you, because if you are using this clock pulse kind of activation mechanism, so if the pulse width of this clock is very high, and in this pulse width, if the set and reset are changing for more than one time, I'm expecting for each clock pulse, the change in the set and reset should be only once. But if the pulse width is very high for the clock, in that case, there is a possibility then the external circuitry can change this set and reset input. There are many reasons. Later on, when I will discuss about the VLSI design, at that time you will get to know like what those sources are. But for now, I will tell you, let us assume like soft error rates. So soft error are one of the possibility that can impact here. So they can flip the set and reset inputs, and if they are changing the set and reset input which are unwanted, so that can create the change at the output as well. Okay, which is the not acceptable or non-desirable kind of state. Okay, so to avoid that thing, I just told you, you can use the age triggered one. So age triggered is, yeah, basically I just told you, because if I have a pulse width which is very high in the level triggered mechanism, so we can do two things. One thing could be like reduce this pulse width, but the problem with this one is like you cannot make it the TD is equal to 0. Yeah, what this TD is, you cannot make it like 0. Okay, and even though if you are able to make it very small, the frequency of the clock will be very high, that is close to infinite. And this is also one of the challenge, you cannot generate a infinite frequency clock. Okay, so this is also problem. So to avoid that thing, the second alternative could be either you can activate during the transition, positive or the negative transition. So to generate this positive transition, you can utilize this differential circuit. So differential circuit is basically that can generate a spike out of the clock pulse. So from the clock pulse to the spike generation is done with the help of differentiator. Okay, and because if I need the positive one, so I need to remove the negative portion. So to remove the negative portion, the diode is the best candidate for the rectification. Okay, so it can pass only positive cycle, not the negative one. So the only positive will be passed, negative will be removed. Okay, so you will get only positive one. Okay, so this is how you can make the positive edge trigger. Similarly, if you have to make the negative edge trigger, so the direction of this diode will be opposite. Okay, opposite direction diode will be utilized to make it the negative edge trigger, something like this. So this will be the actual circuit. Hope you got the answer.
Yes, sir, and also that graph, or you can say the spike that is formed after differential circuit, it has some curve also. So
Yes.
wouldn't that cause problem?
Yeah, see, 100% the glitch cannot be avoided. So what ideally what it should be? Ideally, it should be like the charging time constant should be as small as possible, so that the capacitor should charge, and the discharging time constant should also be as small as possible, so that it can discharge immediately. Okay, and for that purpose you can make the resistance smaller resistance. The smaller resistance will lead to the smaller discharging time constant. So yeah, by adjusting this resistance value, you can make it the slope. You can adjust this slope. So this is possible. You got the point?
Okay, sir. Yes, sir.
Okay, fine. So this is all about the triggering of latches. Okay. Now let us move ahead with other things. Okay. Yes, this is really very important. I just told you there are some differences between the latches and the flip-flops. So let us try to see what those differences are. I just told you the simple difference is like the latches are based on the input in the enable signal, whereas flip-flop are based on the clock in the input signal. So the clock play a major role in the circuit. If simply if you see the second comparison, the block is nothing but latch plus clock, that becomes the flip-flop. Okay, so latch section plus the clock section, that becomes the flip-flop. Basically, because the clock is there, so the clock is basically utilized to synchronize the signals. Okay, so basically the latches are asynchronous one, whereas the flip-flops are synchronous one because of the clock. Okay, so clock are basically utilized to synchronize the elements. Okay, so because in the flip-flop we have the clock, we can synchronize it. Similarly, the triggering mechanism in the latches, they are the level trigger. Okay, they can be level trigger, but in the flip-flop we can make it both level triggered plus edge triggered. Both are possible here. Okay, I think we need to add level triggered as well here. So in the because see here, because we are enabling, we are not making the clock here. So because we are enabling, so just if the enable is high or low, based on whether it is active high or active low, that latch will be enabled. So we can call them this is the level trigger. But the flip-flop can be level trigger as well as the edge trigger. Both is possible. And similarly, like they are sensitive to the level, they are sensitive to the pulse transition if it is the edge trigger. And because to make the clock sensitive, we need to have a more number of gate, more power dissipations will be there. Speed will be slower because we have more number of stages between input and output. So there are some differences between the latch and the flip-flop. Yeah, design is somewhat easier, and for this it is complex because you need to add two more transistors for the clock one. Okay, so it will become the robust one. But one benefit of this one is like noise can create a problem. If there is some noise, then input will be changed, and if it is enabled, so the output will be immediately changed even though it is not activated. But if you are clocked enable and if clock is disabled, so if there is some noise present here, then that noise can be avoided. Okay, and if it is age triggered, so 100% noise can be avoided. Okay, so this is the benefit of the flip-flop. So the noise can affect the flip-flop, like if the clock is activated, clock is active, then the noise possibility of noise is there, and if the edges are there, then there is a possibility. If both are not activated, then the chances of noises are very less. Okay, so the effect of noise on these circuits like the flip-flops are very less. And similarly, these are best used for the non-timing configuration because the clock pulse is not considered, so you cannot utilize this kind of circuits for the timing circuits related to the timing. That they are utilized for the power getting because you know the power efficient devices, and simply you can also use it for the clock storage, like to store the clock you can use it. But if we talk about the flip-flops, you can use this flip-flop for the timing configuration circuits where the timing is important, to make the register. Register is nothing but the group of flip-flop that can store more than one bit. Storage, yeah, simply this is the extended version of the register, and the counter which can count the clock pulses because it deals with the clock, so you can count the number of clocks. Okay, so the counter is also one of the important thing. So these are some of the differences between the latches and the flip-flop. Okay, now let us move ahead with the next thing, which is the different kind of the flip-flop.